We have our first very topic for the day, building planet-scale resilient fintech software, and we have esteemed speakers by our side today. Ladies and gentlemen, please put your hands together for Mr. Anand Rangarajan, Vice President Engineering, Google Bangalore site, Google, and Mr. Kaushik Sridharan, Senior Staff Software Engineer, Google. So,
Thank you. Thanks for this introduction. Thanks so much, folks, for coming. As you folks know, the themes for this GFF are inclusive, resilient, and sustainable. Can you hear us? Yeah. It's okay, right? Yeah. Is in the second theme of resilient, which is what we are going to focus on. And as you can see, the planet scale is someone from Mars is paying someone in India. So we're truly going to talk planet scale in this one. Today being Teachers' Day, I think it's very fitting that we are starting a masterclass. We certainly want to thank all the teachers who have taught us, and we hope we can share some of the learnings we have got in this process. So with that, we'll start the talk. So the first thing is, of course, to understand all these various adjectives, which is planet scale, resilient, fintech, and all these. Do I point somewhere? This one? So here are some things you should know about what we are trying to do in this talk. So for us, massive scale is something which we are always thinking about when we design. It's okay to design some early software which can scale to, say, thousands or a million users. But very soon, if the software is going to be successful, it's going to start looking at hundreds of millions of users. And a lot of the software also has hundreds of services it's interacting with, some of which are built by us, some of which built by our partners. And it's important that when we talk about massive scale, every part of this thing needs to scale. So the weakest link is the one which will be the first thing you'll hit. The second thing is highly available. I think everyone is aware that the 4 nines is a good situation to be, but it still means 52.6 minutes of the year you're down. You're not servicing. So that is something which you should think about. And 5 nines will be really nice. That's about 5 minutes a year. Being down is pretty good. And the other things are things which pretty much every software you think about, you expect. But in the case of fintech, it takes a whole new dimension because some of the transactions which we go through are so critical. If you try to, say, look up who is the captain of the Indian cricket team, right? And if it comes up with, say, the wrong answer or it's not available for a minute or two, it's less impactful on you. But rather, when you're at a shop and you're trying to pay and the transaction is not going through, or it says that the transaction is stuck, and maybe it's gone through, maybe it's not gone through, check in like 2 hours or 3 hours, right? I mean, that's just not a good experience. So what is fintechness about software? How is it different from, say, a Google Photo software or YouTube type of software, right? And what is very important in the case of fintech is, in the case of YouTube, after a person uploads a video, right, we start processing it, we start indexing it, and we start serving it to various users. And a lot of these services are within our own control. But in the case of fintech, there is lots of software which is not owned by a single person who is serving in the request. So there are lots of participants who come in. And then there are issues around, correctness and timeliness. Like you can cache things like, say, who is the Prime Minister of India? But you can't cache things like, what is the balance in your account? So this is something which means that every single thing puts a strain on your system. And some of the simple things which we know about, hierarchical design and caching and all these things cannot be so easily applied. And then, of course, there is things about, data sensitivity. And if anyone has seen the growth of fintech over the last decade, they'll know that, you're sort of always designing for something which is 4 to 10x bigger, right? So I'll just tell you a few things about resilience and then tell you about how every aspect of product development needs to have this capability of resilience. And even if one of that is not showing resilience, it'll show up in the way your software is built and it's used. And the nature of resilience is like what they say about life. A lot of life's own definition is that if you get hit, can you come back up? How well you can come back and how fast you can come back up reflects how good that life is, right? So it's not just about performance when the life is capable, but what happens when the life is hit. And this is true about resilient software too, that when you try to design a system, you should understand that this system will change a lot and it will have a number of unhappy paths. So every piece of software goes through various paths, right? And in lots of other software, the number of unhappy paths is very few. But in fintech software in particular, you'll see there are a number of ways in which this can fail. And the number of failure modes being very high means that you need to be prepared to adjust and change based on that. So I'll just stop there saying that, the pursuit of resilience is that it should permeate every way in which the software is built, designed, deployed, maintained, extended, right? All of these things. Here are some examples which you should be aware of when you think about resilience, right? Usually, when you deploy software and there are services all over, there'll be some small problems in one area, right? Now, how well can you recover from that area? Does it spread very rapidly? These are things which you should know about resilience. I think everyone will be aware of this from the whole COVID experience we had over 3 years, what it means to have a smaller blast radius. The second thing is, how do you handle these various different paths? And I think this is something where I can at least tell you in the case of fintech, we have found that the number of error codes we deal with is significantly higher than the error codes we deal with in some other types of software. I myself worked in, say, Google Search and in YouTube, and the number of error codes we deal with there was just in fintech is just very, very different. And again, we are always like trying to figure out which is your weakest path in this various elements which are in the whole life of a transaction, right? And you're optimizing for it. So at this point, I want to pass on to a very, very competent software engineer. He's a software lead in Google. I have myself, over the last 25 years, led many teams building significantly big distributed system software. But Kaushik is a technical lead who lives and breathes this every day. So at this point, I think it's important for you to hear from him how you design and build for resilience.
Anand. Can I have the clicker? Thanks, Anand. Yeah, so let's talk about how resilience plays a part in, like Anand said, it's part of, it plays a part in every aspect of your software development life cycle. So let's, when you're designing software, for example, oops, wrong button. Okay, so there are 2 points that I want to highlight over here. First is, first you make sure that you designed for extensibility. And what I mean by that is that, fintech is a very fast-moving ecosystem, and you have to be agile to adapt to new business requirements, new product needs. And for that, you really need to have your design such that you leave enough extension points. While you make your design, you don't have to implement everything that you anticipate in the future, but you have to not paint yourself into a corner. So that becomes very important. And secondly, design for failure. See, it's a fact of life. You have to anticipate failure. The failures are going to happen no matter what. You can increase your reliability, but it's something that it may be under your control, or at some point, as you scale, you're going to have failures. And what really matters is how you adapt, how you respond to these failures. And we'll talk about each of these points going forward. So when I talk about design for failure, you have to think about the different failure modes. And by failure mode, I mean the different ways in which the system can fail. I don't mean just your particular service, but the system as a whole. So the failure mode there could be hardware failures, software failures, there could even be human failures, right? So there could be somebody trying to push something out and somebody makes a mistake. And you have to build in resilience at each and every point of that. And for each of these, you have some very well-known techniques. You have redundancy, you have backups. For software bugs, you make sure that you have adequate testing. That's a way to prevent failures. But in the event that you do have a failure in production, make sure that you have the right knobs in production to able to, to mitigate the problem very quickly, to have the right observability built in. And for human failures, you really have to make sure, try to get the human out of the loop as much as possible. For any repeatable task, build in automation, and in case a human is involved, make sure that you have the right documentation and playbooks that are set up so that there's a good process for all of that. And of course, for disasters, and there are well-known techniques. Make sure that if you deploy the latest security updates and so on. All right. So designing for extensibility. It's really important to understand which parts of the systems of your whole system are harder to change. Like, software engineering is really all about trade-offs. You have to make the right trade-offs. It's a judgment call in many cases. But understanding the parts of the system that are harder to change and investing more of your time and effort in those parts becomes really critical. So I have a couple of examples here. Your database schema really needs to be designed well, because once you have data flowing in, once you have tables with data, if you need to make a schema change, if you need to, that's a lot of work. You have to reindex, you have to migrate, you may have to do a data backfill. So that's one area where you really, paying enough attention upfront, doing it early on, really pays dividends. And similarly, your API definitions and your contracts, because if you have to change it at a later point, it's possible, but then you have to, there are other teams that are consuming your API, there's more coordination required, and it's just a lot more expensive. So the more time and effort you put in to define your API contracts upfront, earlier in the design stage, you're going to save a lot of time going forward. And lastly, I'm going to say that you can anticipate requirements changes, but you really don't know what kind of requirements are going to come up. So it's important to keep the gates open, keep the extension points there, but you don't have to design each and every possible feature that comes into that may come up in the future. Just make sure that you don't constrain yourself, don't restrict yourself. So I'm going to take a couple of examples in these. And one example that I have is idempotent operations. If you're not familiar with these words, it's actually pretty simple. An idempotent operation is just something that has the same effect, whether you call the operation once or multiple times. Especially in fintech, this becomes really important. So to give an everyday example, sweeping the floor can be considered to be an idempotent operation, right? If the floor is dirty, you sweep it, you have a clean floor. You sweep it again, the state of the world doesn't change. It still remains clean. So fine, you're doing some extra work, but that's not really a problem, right? It's still a safe operation. Whereas making a cup of tea, if I ask somebody to make a cup of tea, and if I ask that person again, I'm going to end up with 2 cups of tea, right? And maybe that's not too bad, and I would never say no to a second cup of tea. But if that request was for transferring a sum of money, that's going to be a real problem, right? So you really have to make idempotent, the requests that need to be idempotent, you have to build in that capability right from the beginning. And fortunately, it's not really difficult in most cases. So here I have an example where you have the phone represents the client, and that's the server, and it's sending a request to the server. And the server does the processing and it sends a response, but for some reason there's some network outage and the response is lost, and the client times out. Now the client really doesn't have a way to know whether the request was processed but the response timed out, or the request itself did not reach, right? So the client is just going to do a retry. And at this point, if you include an idempotency key, which could just be some kind of a unique ID, that allows the server to decide, to look at the request and say, hey, I have processed this already, I'm done, so just return a success. Or if it's seeing it for the first time, it can then do the processing. So this is a safe way to do it. Of course, you do need coordination between the server and the client, especially if the server is a different party, you need to set up the contracts, right? Make sure that the server respects it. But this is, it's easy to implement, fairly easy to implement, I'd say, but it's very often overlooked in the design phase. So this is one example that I wanted to point out. The other example that I have is that of a database hotspot. And so as you know, for most fintech systems, you have distributed databases where the data is spread across many different partitions or tablets. And if you're not designed your schema and your operations correctly, it's possible that you have a hotspot, which is one partition or one part of the data receives more than the normal traffic, right? So if the data is not uniformly distributed across the partitions, you end up with a database hotspot. So here's an example. The picture on the right is a series of row insertions into a table. And the primary key is shown there. The first part of the primary key is a timestamp, and the next is a user ID. So the way databases normally partition data is they take a range of keys and then they allocate that to an individual tablet or a shard. So if you're using the timestamp, timestamps just keep growing. So once, in this case, the first request goes to the second server, and then the rest of the requests all go to the same server because the timestamp is increasing, it falls in the same range, and then that particular server is going to get hot. The point is, you do have capacity. You have other servers that are not serving traffic, but all the traffic is redirected to that one server, and then you end up with a hotspot. Now, in this particular example, it's fairly easy, again, to solve it. You can just swap the order of the keys. If you have the user ID in the beginning, make sure that you don't have an increasing value as the first part of your primary key. That's one way to avoid it. Another way is simply to hash the unique key so that you can distribute the data more uniformly. Now, let's talk about resilience in the building aspect of software. So firstly, make sure you build simple, modular, and loosely coupled. I mean, this is all, everybody knows this, right? And if you're using microservice architecture, you're already well underway over here. But the advantages really are, if it's modular and if it's loosely coupled, you can evolve those things independently. You have less, each of them can be built and tested separately. So that just builds in more resilience. But like I said, everything is a trade-off. So even when you're using microservices, you do get the fault isolation and the scalability. But there is a cost. The cost is that there's more operational overhead. There's more the overall complexity of the system grows because there are more interaction points. Each individual component may be simpler, but to understand the big picture is more complex. And of course, there's a bit of a performance hit. Things that used to be in process earlier are now out of process. There's a network call involved. There are new failure modes that you need to account for as well, right? There could be a network failure and so on. So everything is a trade-off. That's the key point here. Thirdly, make sure you use known and reliable components. I know the new fancy framework is always tempting. You want to use that. Sure, use that, but make sure you test it. Use it for some internal system first. Know its limits. And once you have gained enough experience with it, then you can go ahead and use it in production. But at least for production critical systems, make sure that you use well-tested systems. And I really like to say boring is good. Like you use a boring system, that's really, it implies more reliability.
We need a little bit more resilience. So maybe some people may want to come this way. We're trying to limit the failure modes here. Thank you.
There's some room there as well. You can.
We are above capacity, but continue.
So this is where it shows up, right? A resilient system you would probably have designed it in a slightly different way. Okay. All right, so let's talk about error handling and observability. And this is something that's often pushed out to later. When you're building a system, you want to get the golden paths right. We'll do the error handling later. That's really resist that temptation. You have to put this on early enough. Have the right error handling strategies. Make sure that you figure out how you're going to, how is it going to be an exception? Are you going to have a error handling routine? Whatever it is, make sure you spend the time there. Make sure you build in the observability right from the beginning. Instrument your code, add logs, add traces. You can, of course, add it later, but then you have lost the context. It's just more expensive to do it. And finally, at Google, we have a very strong culture of code review and testing. And I've worked in other companies which did not have that. And it may seem like a lot of overhead, but really, that's probably one thing that has made the biggest difference. Having another person look over your shoulder, review the code, say, it looks good, that really makes a huge difference. And so build that into your processes. Code is normally read way more often than it's written, right? Optimized for the reader. It's going to live more longer than, people move. Make sure that code is, you optimize for the reader. Choose names carefully. I've seen more time wasted because there are two groups of people talking about the same thing. They're just using different names. And it just spends time in choosing the right names, and have a glossary. If you can, write a glossary, publish it, make sure that people can look up names. And yeah, code is a liability, especially untested code. The stuff that the code does is an asset, but code itself is a liability. So like Anand said, at GPay we interact with many, many different partners, and each of them, multiple APIs with multiple partners, and each of them have different error modes, different sets of failures. And it's not a static set either, right? They add new APIs, they have new error codes. So this is something that we have learned where we move to a config-based error mapping system, which we can deploy without having to do the full production deployment. And this configuration is organized by a high-level category for each error code and a fine-grained category. And you can look up whether is it retriable or not? Is it a technical decline? Is it a business decline? Is it an internal, external error? So all kinds of breakdowns. And it's organized by partner and the particular API. And we've built a process around updating it. So whenever we get new sets of new error codes from our partners, we have a well-defined process where they can add it to their configuration and pushed out. So that's really something that we have learned. It really helps in the long run.
Just 1 second, Kaushik. Just wanted to add one thing on this naming thing. You folks might think that this is too simplistic a thing, but I'll tell you, when I was at YouTube, there was an actual outage which happened because there were 3 words, segment, fragment, and shard, which were used in the code. And someone just assumed that they all were synonymous when one of the designers expected a segment to be something which is specifically within one data center, not spread about, and someone just decided to violate that. And this is a classic problem where if you don't consolidate on clear terminology, somewhere in the code, someone will assume that, yeah, these are synonymous, it's okay to use this, when actually it's not okay. Just wanted to tell you that as an example.
Yeah, I don't know if you guys follow the domain-driven design. If you've read that book, there's a whole section on ubiquitous language. I think that's part of it, making sure that you have a published clause and so on. So message queues are, I'm sure pretty much every fintech system has to use this. If you want your calls to be reliable, you want to be able to do retries. And oftentimes it's pretty much, you have to use message queues. You get more reliability. It also gives you the ability to do deferred processing if you want to take some action at a later point of time. But there are some things I want to highlight you have to be careful about. You must have good error handling in your message receiver. Otherwise, there's a potential of unbounded message queue growth, and that becomes extremely difficult to debug once you're in that situation. So make sure you avoid that. Understand the guarantees that your message queuing infra gives you, right? Does it give you ordering guarantees? Does it give you deduplication guarantees? If not, you have to build it on your own. And make sure that you're able to update the payload schema in a way that's forward and backwards compatible. Because you can't empty the queue. You have to do it on your queue already has some messages, and if you need to update the schema, there should be a way to do it. At Google, we use something called protocol buffers, which has well-defined semantics for compatibility, and that's helped tremendously. If you're using protocol buffers, make sure you'll go through those compatibility rules. If not, just make sure that whatever other transport you're using, use it in a compatible way. And one last tip I have, which is related to the idempotency slide that I had before. Think of your operations as a desired state rather than as an operation. That kind of implicitly gives you the idempotency. Make sure that get into this state rather than do this, transfer some money or deduct a fee. So if you're using message queues, you have to do retries. And this is something that you also have to think very carefully about. It's very easy to completely overwhelm a system, your downstream system, especially if it's an external partner, just because you have a bad retry strategy. Because you may have an outage and you're just going to have a backlog, and then you just don't want to keep hammering your downstream. So exponential backoff is a commonly used technique. So as the saying goes, if at first you don't succeed, try again, but use exponential backoff. And preferably with some randomized jitter to it. I'm going to go over testing fairly quickly. Most of this is obvious. Make sure you test it at all levels: unit test, integration tests, end-to-end tests, system tests. Fast testing, especially for security issues, is a very good technique. Make sure you use automation. Use a CI system if you're not already using one. And make sure you test all the unhappy parts as well. You tend to test the golden parts, but the unhappy parts, all the errors, each and every error scenario should be well tested. And don't let your flaky test accumulate. Over time, it just becomes extremely difficult to clean them up. These 4 points are, these are actually learnings we had as part of Google Pay, as part of building Google Pay. Integration tests are absolutely critical. I can't stress this enough. There are so many partners involved. Invest in good, stable integration tests. Maintain a stable UAT environment, a user acceptance testing environment. It's an investment, but it's really worthwhile. Make sure you have a stable one. If you're working with other partners, kind of insist that they have a good UAT environment. Build the ability to simulate error scenarios and latencies. In GPay, we have built a whole simulator system which lets us inject different kinds of errors, different latencies, different error scenarios. And that helps, things that otherwise won't be found until you actually push to production. And load testing, like Anand said, you have to plan for at least 4x growth. That leaves you enough room to, once you plan for it and you account for it, then that gives you some buffer space in which you can innovate and actually build on the features. Otherwise, you are in this constant loop of, extending, load testing and extending. So when you do it, build up some buffer so that you have some room to grow. So when it comes to deployment, again, automation. This is extremely important, especially most of you are in companies that are growing. It's just going to become harder if you have people involved. Try to automate as many things as you can. If you're using a CI/CD, a continuous integration, continuous deployment pipeline, you're already in good shape. Treat configuration as code. Configuration changes should go through the same review process, should go through the same version control process. Don't treat it as second-class citizens. In spite of all this, in GPay, we've probably seen more errors, more production errors because of bad config push, right? Even with all good intent, it still happens. So there's something to be very careful about. And when you're deploying software, whether it's automated or manual, make sure you're monitoring it after the fact. Feature flags are something that we use at Google to deploy software incrementally and as well as enable features at a later point of time. So we can time the launches. Every new feature is put under a feature flag. And you can also enhance it with, like we also have something called experiment flags, which allows us to roll it out, ramp it up slowly. We first ramp it out to 1%, 5%, and ramp it out to particular user cohorts, which lets us observe how it works in production. And then you can gradually ramp up. And again, don't leave stuff lying around, clean up afterwards. Canaries is something that we use at Google. It's a technique where when you're deploying a new version of your software, you first deploy to a small subset. So the green boxes represent the new versions that are deployed. And then you watch. You evaluate how well it's working. And at a later point, you make a decision on whether to deploy the whole thing. Again, this is all automated. No one is actually looking at it. So it's basically an early warning system. If your new code introduces latencies or, those are the things that you have to watch out for. So firstly, you have to figure out whether the canary population is representative. Secondly, make sure you use the right evaluation metrics, latencies, error rates. And finally, you have to make the decision on, it's also called blue-green deployment in certain cases. So that's slightly different because here the canary population is smaller. It's called canaries because in the old times when people used to work in mines, they used to carry a canary with them into the mines. Because if there are any toxic fumes, the canary would feel the effects much quicker because of the faster breathing rate. So it's essentially an early warning system. Okay, maintaining. You can sense a theme here, automate. The more you automate, the better it is. Observability, you have to build in monitoring, logging, tracing. Monitoring lets you can see graphs on how different parts of the system are performing. Add alerts on top of those graphs. And tracing gives you a cross-server view of a call. Otherwise, you're always looking at the state of a given server or a service. Tracing gives you, as the request flows through multiple layers, it gives you that view. So that's important. Automate every task that's repetitive or error-prone, including deployments, config pushes, testing. And if you do have an on-call rotation, make sure you have a good playbook, good checklist that you can follow. Cascading failures are one category of failures that happens. If it happens, it's really difficult to debug because there's a failure in one part of the system and there's a ripple effect that flows through the system. And you don't notice it until the symptoms start showing up in a different part of the system. So by the time you see it, the root cause is really hard to find, right? And it can grow very rapidly and it's really difficult to debug. And it's usually caused by resource exhaustion, although there are other cases where it happens. And here's an example. It starts with the front end having poor garbage collection, poor tuning for the garbage collection. And that causes a series of problems on the front end. And it's going to take more RAM. And then that's going to reduce the available cache size for the front end. And that puts more load on the back end. And then the back end start getting killed. And that's where you notice it. And by the time you notice it, to trace your way all the way back it's just extremely difficult. So there's something to watch out for. And all the things that I mentioned before, the observability, help in detecting and fixing these. So to prevent it, firstly, test your components to failure and beyond failure, right? Know the limits of your system, where it breaks. Usually there's one weak link, you have to know what that limit is. You can use rate limiting on the client or the server to throttle the rates at which requests are sent. To mitigate, the first thing you do is you increase resources, right? But at some point, you may have to make the decision to actually drop user traffic, right? You're going to just throw some requests on the floor. And that is bad. I mean, not just sounds bad, it is bad. Some users are not going to get serviced over there. But if you don't do that, you're going to bring the whole service down. So that's again a trade-off that you have to make. You bring the system back to a stable state, and you may even enter some degraded modes. So finally, I want to talk about incident management, which is the process. If there is a production outage, what is the process you follow, right? And in the world of aviation, this is a saying: aviate, navigate, communicate. This is part of the training of every pilot, right? Everybody knows this, if you're in the aviation world. And the idea is that in case there's an emergency, the first thing you need to do is keep flying your plane, right? There have been instances where people the pilots have gotten fixated on some blinking light in the cockpit, and then they forget to fly the plane. So the first order of business should be to aviate, then navigate to a safe place, and finally communicate with the air traffic control. So for incident management, there's a similar pattern. Your first order of business should be to mitigate, right? Try to reduce the user impact. Don't get into the debugging mode. First, mitigate the system. Get the system running again. You have to keep communicate with the other people who are all your stakeholders. And you can leave the investigation for later. Collect records, keep detailed records, but make sure that you are actually mitigating the problem first. And finally, we talked about all these things on how to build resilience into a software system. But culture is really the way in which you build resilience into the company, right? That's how your company, your organization becomes more resilient. And here are, make sure you evangelize reliability within your company. If you're an engineer, make sure, if you're an engineering leader, you make sure you allocate the right resources, prioritize it. If you're not in the position to make that call, it's still your job to convey the information about, make sure that your leadership is fully informed about the state of your reliability so that they can make the right calls. Don't hide bad news. This is, absolutely, if a system is wrong, if something is not running right, it should be part of the company culture so that bad news is not hidden. And finally, at Google,
one way, by the way, this is framed as bad news takes the elevator, good news takes the stairs. So this is a common thing you will hear.
Yeah. And it has to be part of the culture because, if any one point does not transmit the bad news, it's just, you're just never going to get it. And at Google, we follow something called blameless postmortems. A postmortem is basically, when there is a production issue, there's a written record and a meeting that we have. We talk about what went wrong, how we can avoid it in the future, more importantly. And the blameless part is really important. You should focus on the problem, focus on the action items, focus on how you can make your system stronger. It's not about finger pointing, right? The whole point is that you have to emerge much stronger out of the postmortem. So this is something that I would really encourage all of you to adopt in your organizations.
Cool. So I think we are.
Yeah, I have some resources. These are books. You can buy them, but also they are available online for free. The first three are more about reliability. The last one is a more holistic software engineering, how it works at Google. You can just go to those URLs and the entire book is available online.
Yeah, so this is some of the material we have planned to share with you folks. We're happy to take few questions. One or two, and we'll finish. I will tell you this, though, before the questions, that, folks, we have shared a bunch of things here, okay? Almost every single thing which we have shared here has a bad story behind it. Like, we didn't do something, and that caused some outage in some form, okay? And which is why it's here. But I'll also tell you this, that even having gone through this whole experience, at any point of time in Google, probably there's only like 70 to 80% of software which follows all of these things. And software is at different stages. There are software which is like 20, 30% stage. They're just starting, they haven't covered many of these bases. And then there is software which is at like 95% stage. Very, very mature, heavy load every day. There's just no choice. The chance of making a mistake is very, very, very expensive, right? So just want to tell you folks that we're not here giving some gospel that we are doing very well.
Yeah, we are all learning. We're
Yeah,
all learning here.
we face these challenges every day. But I do think the culture part is the one thing which every one of you should take. That if you can create a resilient culture, it can go out and address many of these resilience issues one after another. And that's very, very important. One or two questions, anything which we can share? Anybody? Yeah.
Hey, hi. So I'm a little interested in how do you build observability in systems, network systems like ONDC or UPI, right? Where you have external interfacing systems, you have no control over, right? So how do you build observability? And the second question is, you talked about the idempotency using a key, right? How do you maintain that key on the server side? Do you write to disk or do you cache it? How did you actually solve it in your case?
Yeah, so the second part first, we usually serve to disk, but you can also cache it. It's either way is fine. If you know that your window is small, you can cache it. But typically, we just serve to disk. On your first part, that's actually a really challenging problem because you have external parties and you don't always have the visibility. So, firstly, develop if you have build good relationships with the engineering teams over there. That's one way. But again, you are not going to have the same granularity of metrics that you have about your own system. So, I mean, you can add the right logging and tracing in your system, but at some point there's going to be some kind of a blind spot, and there's not much you can do about that.
Yeah, but for the first question, I mean, the standard technique people use is you have your own grids for every transaction which you want to be able to debug. They have their own grids and everything, so there has to be mapping at every point for you to trace this thing all through. I think Kaushik talked about how we do it internally.
Yeah.
And the only way to do it outside is to have all these mappings of grids. And the trickier part here is how do you maintain data privacy and security while still being able to do this correlation? That is where you'll need to work through, what data are you going to share as a part of this debugging process, what data do you keep?
So typically you're writing to disk anyways. Usually the operation involves some write, so you're not adding that extra idempotency key is not adding an extra cost. Usually you can just make it part of your normal write in most cases. Yeah.
Yeah, just to follow up to that, managing it internally is okay, but how to handle the idempotency when the request is coming from your front-end clients, let's say, because there might be multiple network failures and stuff.
Yeah. So you can still, the front-end client can still choose a random key. They don't, the generator of the, yeah, yeah.
I don't know how the
If the same client is sending two requests, then they can maintain the same. The client knows if it's making a second request or not. The retry, the client usually knows. On the server side, it's what you don't know.
Yeah, but let's say there's a network failure and retry happens.
If it's the same client that's doing the retry, they can still use the second request with the same idempotency key.
Let's say create order, a payment.
Yeah.
Yeah.
It's very important. So somebody is just clicking two times, it will be a two.
Yeah, but the client is sending the request to the server. So the client, even if it's sending it the second time, firstly, your UI should block it. If it doesn't block it, there's still, you can have some heuristics. If it happens within like half a second, it's likely to be a duplicate request. But usually in this case, that the multiple clicking, the problem is really somewhere else. That's something that you have to work on.
All right. Yes. Thank you, gentlemen.
Thank you so much.
Thank you so much.
That
folks.
brings us to the end of this session. Please put your hands together for our esteemed speakers once again. And thank you, our dear audience, for joining us today.